Hello guys, welcome to Self-Help Maths Academy. Today I'm going to discuss about the algebra of limits. Algebra of limits. So in this, we will start with, we have a theorem or the result. Say let f and g be two functions and a be a point of their common domain. Okay, then if limit of f of x as x is tending to a is equal to L and limit of g of x as x is tending to a is equal to m, then we have, say the first one, let us try to prove it one by one. Limit f of x plus g of x as x is tending to a is equal to L plus m. So let's start prove one by one so that we will understand it in a better way. So here what happens is, we need to prove they have given that the limit of a given function as x tends to a is equal to n, the limit of g of x as x tends to a is equal to m. We know by the epsilon delta definition of a limit. So we'll start our proof. Given limit of f of x as x is tending to a is equal to, say, L. Whenever they say that there is a function, limit of that function as x tends to a is equal to L, it implies for a given epsilon, okay, greater than 0, there exists, say, some delta 1 which is greater than 0, such that the modulus of f of x minus L, the difference between the function and its limit value, is less than epsilon by 2. This is true for all 0 less than modulus of x minus a, which is less than delta 1. So this is actually the definition of a limit. This is called epsilon delta definition of a limit. Similarly, they also told us, they are also given that the limit of g of x is equal to m. So limit of g of x as x is tending to a is equal to m. This implies, again by using the definition of a limit, given epsilon greater than 0, there exists delta 2 greater than 0, such that we have difference between g of x minus m is less than epsilon by 2. Okay, less than epsilon by 2. This is true for 0 less than x minus a, which is less than delta 2. Say this is equal to equation number 2. So now we have equation number 1 and we have equation number 2. So this is with the help of the definition of limit. Okay, now what I do is, I will take let delta be, because we have a delta 2 here, we have a delta 1 here. I define my delta as minimum of delta 1 and delta 2. Then from 1 and 2, we have modulus of f of x minus L is less than epsilon by 2 and modulus of g of x minus m is less than epsilon by 2. These two results are true for 0 less than modulus of x minus a less than delta. I'm not taking delta 1 or delta 2. I'm now taking it as a delta. Okay, because my delta is what? Minimum of delta 1 and delta 2. Okay, all right. So now what we do, we have taken the minimum of both delta 1 and delta 2 and we have used it in this particular final result here. Okay, so now let us start with I'll add both. So f of x plus g of x minus, say, L plus m. Let us consider this. So this is equal to, I can write here separately, modulus of f of x minus L, okay, like this, as a separate bracket, and then plus g of x minus m. Okay, So we know that modulus of x plus y is less than or equal to modulus of x and modulus of y. So I'll separate the modulus here, plus g of x minus m. Okay. But we know that what is f of x minus l? Modulus of this is less than epsilon by 2. Modulus of g of x minus m is less than epsilon by 2. So let us substitute that value here. So this will be equal to, which is less than, say, epsilon by 2. Epsilon by 2. Okay. So this is nothing but what? Epsilon. This is true for 0 less than modulus of x minus a, which is less than delta. We started with, if you see, the limit of f of x as x is tending to a, if it is equal to L, means we know that it is modulus of f of x minus L is less than epsilon by 2. Now what we got, if you observe carefully, we have got here f of x plus g of x minus L plus m is less than epsilon. So that means your this function tends to the limit L plus m. Okay, this is true for all this x minus a less than delta. So hence we conclude that this implies limit of f of x plus g of x, this as x tends to a, is equal to L plus m. So this is what we wanted to prove. This is one of the algebraic property of the limit. So similarly, they also we are also interested in the property. Suppose limit of f of x minus g of x we have, as x is tending to a is there. This is equal to L minus m. This is equal to L minus m. Okay. So now in order to prove this, we will proceed in the same fashion. But instead of that, we will just take here f of x minus g of x, then minus, yeah, this will be L minus m. So please use the bracket here because as it has a negative sign. So this will be equal to modulus of f of x, this minus L here. Okay. So in short, if you see, it is minus of minus plus here, plus m minus g of x. Okay. So this is what we are getting. Now what we do, we can write this as a separate bracket. So this will be less than or equal to modulus of f of x minus L plus modulus of m minus gx. Okay, so as you know that in the modulus, whether the quantity is positive or negative, you take inside that modulus, it will be always positive. So hence I can write this as modulus of f of x minus L plus I can write this as g of x minus m. Okay, so now we know that this is also less than epsilon by 2. This is also less than epsilon by 2. So epsilon by 2 plus epsilon by 2. So which is equal to epsilon. This is true for 0 less than x minus a, which is less than delta. So therefore now we got this quantity is less than epsilon. Hence we can say that limit of f of x minus g of x as x is tending to a, this is equal to L minus m. This is equal to L minus 1 m. So this is the proof of this particular result. Okay. So now similarly, let us see the multiplicativity. Okay. Also we have a result that says limit of f of x into g of x as x is tending to a is equal to L into m. This is also we have to prove. So to prove this result now, let us start with the given, condition. So we know that limit of f of x as x is tending to a is L. Okay, so this implies for a given epsilon 1, I take greater than 0, there exists delta 1 greater than 0, such that modulus of f of x minus L is less than epsilon 1 for 0 less than modulus of x minus a, which is less than delta 1. So this is by the definition of limit. Okay, let us take this as say 1. Okay, now similarly they have given a limit of g of x is equal to say m as x is tending to a. So this implies here given as we have given with both epsilon both g of x and f of x and g of x. So therefore you need to take for both. So here for a given epsilon 2 say greater than 0, there exists some delta 2 greater than 0, such that modulus of g of x minus m is less than epsilon 2. Okay, this is less than epsilon 2. This is true for 0 less than modulus of x minus a, which is less than delta 2. Let us take this as some equation 2. Now we will choose our delta. Okay, let us choose our delta, which is a minimum of your delta 1 and delta 2. Okay, so it's a minimum of say delta 1 and delta 2. All right, so now we have taken our delta as a minimum of delta 1 and delta 2. All right, now let's see. We will have the required result, that is from this when I take this one. So therefore our results will become f of x minus l, the limit of function, this will be less than epsilon 1, and we know that g of x minus m is less than epsilon 2. This is true for 0 minus x minus a, which is less than say delta now. Okay, so now with this, if you observe carefully, we will have let us try to take now the f of x minus, this one will be this. From here we can write this g of x as say modulus of g of x will be equal to, if I can write this as modulus of g of x minus m plus m. Okay, I'll write this way. This will be less than equal to modulus of g of x minus m plus modulus of m. This is just the adjustment. So we know that this is nothing but our epsilon 1, sorry, epsilon 2. So we can write this as less than epsilon 2 plus modulus of m. So this will be epsilon 2 plus modulus of m will be less than 1 plus modulus of m, because you know that your epsilon by 2 is greater than 0. It is a small positive number, so of course this has to be less than 1, and therefore I'm taking this as less than 1 plus modulus of m. So here clearly you have got modulus of g of x is less than 1 plus modulus of m. Okay, so we have got this. Now I'm going to use this one in my upcoming result, that's why. So now what we do, now I will take modulus of f of x into g of x minus l m. Okay, we'll start with this because that's what we want in the result. So this will be equal to, let me write this as modulus of f of x into g of x. Here I will add and subtract with l into gx. So there will be no issue if I do so, minus lm. Okay, so this will be equal to, so from here if you observe, from these two terms I can take the g of x out, and from these two terms I can take this L of x. Okay, so for what I will be doing here is I'll take this g of x out. This I am left with f of x minus L, and here I'll be taking L out, so this will be g of x minus m. Okay, so here yeah, so this will be now like separate the modulus. With the help of that we can write this as modulus of say g of x and modulus of f of x minus L. Okay, then this is modulus of L and modulus of g of x minus m. All right, so as we know, modulus of g of x from here we calculated that as less than 1 plus modulus of m, so I can include that, which is less than 1 plus modulus of m, and this we know the value, this is nothing but our epsilon 1. Okay, so let us use the brackets here, and this I'll write as modulus of L, and then I know that this value is epsilon 2. So this is true for 0 less than modulus of x minus a, which is less than delta. Okay, so we have got this one. Now what we do, now taking since we started with this na, so we have to achieve that this value should be less than epsilon. So for that, no, what I'll do is I will try to, you see this one is L plus modulus of m. I choose my epsilon 1 in such a way that I should cancel with this, and I'll be getting here epsilon by 2. So for that what I do, I'll choose my epsilon 1 by say epsilon upon 2 into 1 plus modulus of m. If I take this, if you observe, this with cancel with this, and I'll be left with epsilon by 2. Similarly, our epsilon by 2 will be equal to, as you see here in this case, you have got modulus of L here. So what I do is I'll choose my epsilon by 2 as epsilon upon 2 into 1 plus modulus of L. Okay. So therefore what we have now just substitute it here. So we started with modulus of f of x, g of x minus Lm which is less than equal to, this is 1 plus modulus of m, and epsilon 1 will be epsilon upon 2 into 1 plus modulus of m, plus this is modulus of L here, epsilon by 2 is epsilon upon 2 into 1 plus modulus of L. Okay, so now here we can cancel this one. We can cancel this one with this one. Okay, so this will be cancelled. So we are here, we are good with, if you observe here, we are good with, this is equal to we are left with, say, less than epsilon by 2, and this is here modulus of L upon 1 plus modulus of L into epsilon by 2. Okay, as you know that this is modulus of L, and divided by 1 plus modulus of L means this is still less than 1, and this is also less than 1. So therefore the whole quantity, I can take this as epsilon by 2. So epsilon by 2 plus epsilon by 2, which is equal to epsilon. So this is true for every 0 less than exponential, which is less than delta. So therefore by the property of the limit, so we are now good here. So hence we started with this one, we got that is less than epsilon. So therefore we say that limit of f of x g of x as x is tending to a is equal to L into m. So this is also very important result in the algebra of the limits. Okay, so now we are having one more result where we will be proving that the division of a given limit is also, like, obeys this particular property. Let's see that. Now to prove the next property, which is limit of f of x upon g of x as x is tending to a is L over m, provided m is not equal to 0. So to prove this, we will start with, again, given. Now let us prove this to prove that result. Now let us prove first the g of x is equal to m, and we'll start with this one. Say limit g of x as x is tending to a is equal to m. This is given that it is not equal to 0. This implies if g of x is not equal to 0, then 1 over g of x limit as x tends to a, it will become 1 over m. Okay, so therefore you know that now limit of g of x as x is tending to a is equal to m implies, by the definition of limit, given epsilon greater than 0, there exists delta greater than 0, such that difference between g of x minus m is less than epsilon. This is true for 0 less than modulus of x minus a, which is less than delta. Okay, now I will take my modulus of m as, okay, let me take the modulus of m as, I'll write this as, say, m minus g of x plus g of x. Okay, there will be no problem if I write that, because g of x cancels, I still have the same. So this will be less than or equal to modulus of, say, m minus g of x, okay, plus g of x. I just separated this one and then this one. Okay, so now what we have, this is equal to, as you know that whether it is m minus g of x or g of x minus m, in the modulus it is one another same, because it is a positive quantity. I'll write this as g of x minus m, plus I'll write this modulus of g of x. Okay, this is actually, this is nothing but less than, you can see this, this you started with by the limit definition, this that modulus of g of x minus m is less than epsilon. So this is epsilon plus modulus of g of x. This is true for 0 less than modulus of x minus a, which is less than delta. Okay, now this implies your g of x, modulus of g of x, okay, your modulus of g of x will be greater than modulus of g of x will be greater than modulus of m minus epsilon. Okay, your modulus, if you observe carefully, your modulus of g of x will be greater than, because this is less than this, therefore modulus of g of x will be greater than modulus of m minus epsilon. So this is also true for 0 less than modulus of x minus a, which is less than delta. Now what we do, we taking epsilon is greater than modulus of m upon 2. Okay, we choose our epsilon in such a way that it is modulus of m by 2. So we get modulus of g of x. See here, modulus of g of x will be greater than. So this is modulus of g of x is greater than modulus of m minus epsilon. My epsilon is modulus of m by 2. So it is modulus of m minus m by 2 will be what? It is m by 2. If you want one more time, you can write modulus of m minus modulus of m by 2. This is equal to modulus of m by 2. So now modulus of g of x is greater than modulus of m by 2. This is true for 0 less than x minus a, which is less than delta. Okay, so this implies, since we know that this also, if g of x has a limit, so 1 upon g of x is 1 by m, right? So now therefore what I'll do is I will just take 1 over modulus of g of x. Okay, so this will be less than this, because we have it as like modulus of m by 2, it will be, when I reverse, it also reverses, so 2 divided by modulus of m. This is also true for 0 less than modulus of x minus a, which is less than delta. Let us take this as sum 1. Again we have g of x limit as x tends to a is equal to m. This is true given. Now I'll choose my epsilon 1 is equal to modulus of m square upon 2. So be careful when I'm choosing the epsilon values. Okay, it is like, as per the choice of the proof. Okay, so it is like I'm choosing my epsilon 1 as, say, modulus of m square upon 2 into some epsilon which is greater than 0. So therefore there exists delta greater than 0, such that modulus of g of x minus m is less than epsilon 1. This is true for 0 less than modulus of x minus a, which is less than delta. Okay, so now let me take this as sum 2. Okay, now what we do, we will try to take the difference between them. So 1 over g of x minus 1 over m. So this we will take. This we can write it as, if I take the LCM, it is m minus g of x upon m into g of x. Okay, so this is equal to g of x minus m, because it is modulus. So we know that modulus of x by y is modulus of x divided by modulus of y. So here we can write this as modulus of m into modulus of g of x. Okay, so here if you carefully observe, we know that g of x minus m, this modulus of function will be less than epsilon 1. Okay, and we know that modulus of m is here. This is the modulus of m, and then we have got modulus of g of x, that is nothing but 2 over modulus of m. So by writing that, we will get it here is equal to, we will write it here, that is equal to modulus of epsilon 1 divided by modulus of m into, this is modulus of g of x is 2 over modulus of m. So we can write this as g of x is equal to into 2 divided by modulus of m. Okay, so this is again true for 0 less than x minus a, which is less than delta. So now this is equal to, here you can see this is 2 epsilon 1 modulus of m will be modulus of m square. So here what I get, epsilon also you know that your epsilon 1 is modulus of m square upon 2. So I'll just write that as modulus of m square upon 2. And this, there is a modulus of m that will be also 2 divided by modulus of m square Okay, so here you can see this cancels here, this cancels, this cancels, and this cancels. You're just left with what? Because this is into epsilon is there, so this you're left with just epsilon. Okay, so this is that is nothing but what you started with. You started with modulus of you started with 1 upon g of x minus 1 upon m. This you got it as less than epsilon. This is true. This is true for 0 less than modulus of x minus a, which is less than delta. So therefore limit of 1 upon g of x as x is tending to a is equal to 1 over m. So now we wanted limit of f of x. We wanted limit of f of x divided by g of x as x is tending to a. This we wanted. This is equal to limit of f of x as x is tending to a into 1 into 1 upon g of x. Okay, so this is nothing but limit of f of x as x is tending to a into limit of 1 upon g of x as x is tending to a. So this already we know, this is L, it is given, and this we know that it is 1 by m, just now we proved. So therefore this will become L over m, where m is not equal to 0. So here important part is we are not started with the direct function what is given, but we try to prove with the g of x g of x function, and we concluded that this 1 over m, where m cannot be 0, and we try to prove that 1 over g of x as x tends to a is equal to 1 over m. If once we prove this, right, then it is easy, and it's very clear to prove the remaining results. So this is very important. How do we come across this particular point in order to prove the algebra of the different limits? So here in this particular discussion, we have done the algebra of the limits. Okay, so this is very important. I think I'll be solving the examples in the next video. Okay, till then, take care guys.